Hello friends, welcome back to my YouTube channel. This is the 15th part of my discussion on molecular diffusion through fluids. And today I will be talking about diffusion coefficients for liquids. How to estimate diffusion coefficients for liquids. In past few video lectures, I have been talking about diffusion coefficients for gases. I had told you how you can estimate diffusion coefficients for gases. Now let us understand how to estimate diffusion coefficients for liquids. So in this video lecture, I will be discussing few equations that are available in the literature for calculating diffusion coefficients for liquids. So let us begin the discussion. First of all, let us understand what is a diffusion coefficient. For that, we need to know Fick's first law of molecular diffusion, and we can understand this law by considering a solution of two liquids, liquid A and liquid B. And if you consider molecular diffusion of E in this solution in the Z direction, then the mathematical statement or mathematical expression for Fick's first law of molecular diffusion is like this. Ja is directly proportional to dabba Ca by dabba Z. So here the law is written in the law, or in the mathematical expression we have used partial derivative. So this indicates that diffusion can also happen in the other two directions, X and Y direction. So according to Fick's first law of molecular diffusion, Je, I will tell you shortly what is Je. You already know it. I have already discussed Fick's first law of molecular diffusion in details. I am giving link to the entire playlist of my video lectures on molecular diffusion through fluids. The link is available in the description section. So according to this law, Ja is directly proportional to dabba Ca by dabba Z. The partial derivative indicates that we have considered diffusion in Z direction. Diffusion also occurs in the other two directions, X and Y direction. So if you remove the proportionality, the equation will be written like this. Ja is equal to minus dab dabba Ca by dabba Z. And if you ignore diffusion in the other two directions, X and Y directions, then this partial derivative can be replaced with a total derivative. So it will be Ja is equal to minus dab dCa by dZ. So in this equation, Ja is molar flux of E, molar flux of liquid A relative to the molar velocity of liquid B. Again, I have discussed this in detail in my video on Fick's first law of molecular diffusion. Then dAb in this equation, it is a constant, proportionality constant, and this constant is called the diffusion coefficient or diffusivity of A in B. The negative sign in this equation indicates that the molecular diffusion, or A, diffuses from a place of high concentration to a place of low concentration. So in order to indicate that, we have the negative sign in this equation. The negative sign indicates that diffusion is taking place from a place of high concentration to a place of low concentration. Or you can say A diffuses from a place of high concentration to a place of low concentration. Then dCa by dZ in this case is the concentration gradient in the Z direction. So how concentration is changing along the Z direction, it is described by this term, dCa by dZ. This is concentration gradient in the Z direction. So this is the first law, Fick's first law of molecular diffusion, which has the mathematical expression for this law has a proportionality constant, and that proportionality constant is nothing but the diffusion coefficient, or you can also call it as diffusivity. Let us move ahead. Fick's first law of molecular diffusion we just saw. Ja is equal to minus dAb dCa by dZ. Now, if you just consider the magnitudes, that is the direction of diffusion, if you ignore, you can simply write the equation like Ja is equal to dAb into dCa by dZ. And from this equation, you can write an expression for dAb. So, dAb will be equal to Ja upon dCa by dZ. So, as per this equation, dAb will be equal to Ja if dCa by dZ, is 1 according to this equation, then dAb is simply equal to Ja. So that will help us in defining the diffusion coefficient. So you can define it like this. The diffusion coefficient, one way is you can call diffusion coefficient as the ratio of molar flux to the concentration gradient in the given direction. This is one thing, one way of defining it. So you can also define it, or you can also understand in this way. Diffusion coefficient is the molar flux that results due to unit concentration gradient in the given direction. So that is, if dCa by dZ is 1, then dAb is equal to Ja. So you can understand diffusion coefficient as the ratio of the molar flux to the concentration gradient in the given direction, or you can say that it is the molar flux that results due to unit concentration gradient in the given direction. So let us move ahead. Now we have defined diffusion coefficient. So we have got an answer to this question. What is a diffusion coefficient? Let us move ahead. Now let us know what are the dimensions for diffusion coefficients. So we have the equation dAb is equal to Ja upon dCa by dZ. We have just understood or got this equation. So dimensions of dAb will be equal to dimensions of Ja. And what are dimensions of Ja? Kilomole L raised to minus 2 T raised to minus 1, because molar flux, unit for molar flux is kilomole per meter square per second, or it could be mole per meter square per second. So it is kilomole length raised to minus 2 and time raised to minus 1. Whereas the dimensions for concentration, molar concentration, they are kilomole. Molar concentration is kilomole per meter cube, for example. So this is, the dimensions are kilomole L raised to minus 3, and dZ, which is in distance in the Z direction. So dimension for that is L. That means dimensions for dAb are, if you simplify this, it will be kilomole L raised to minus 2 T raised to minus 1 divided by kilomole L raised to minus 4. This L, when it comes on the in the numerator, it will be L raised to minus 3, L raised to minus 1. So it is L raised to minus 4. So therefore dimensions for dAb, we are left with kilomole will be getting cancelled, and you are left with L raised to 2, because this is L raised to minus 2 plus 4. So that is L raised to 2 and T raised to minus 1. So dimensions for diffusion coefficient are length square into time raised to minus 1. And if you have to talk about the units, let me erase this. I hope you have understood it. If you have any doubt, you please let me know. Then units in different system of units. In SI system, The units for diffusion coefficient are meter square per second. In CGS system, the units are centimeter square per second. In FPS system, the units are feet square per second. But mostly diffusion coefficient in literature, they are reported in centimeter square per second. So in SI system, the unit is meter square per second. In CGS system, it is centimeter square per second. Mostly diffusion coefficients in literature are reported in centimeters square per second. And then in FPS system, the units are feet square per second. Now, diffusion coefficient, if you have to understand it in a different way, you can say that it is a measure of the mobility of a substance by molecular diffusion. Talks about diffusion coefficient, talks about the ability of a substance to move by molecular diffusion, to transfer by molecular diffusion. So diffusion coefficient, it is a measure of the mobility of a substance, mobility of any substance by molecular diffusion. Diffusion coefficient, it depends on many parameters. It depends on the nature of component. For example, in a solution of A and B, it will depend on nature of A and nature of B. Then it depends on temperature. It depends on concentration. And as far as pressure is concerned, for liquids, the diffusion coefficient is almost independent of pressure. And what is the reason for that? Liquids, we consider liquids to be incompressible. So as liquids are considered to be incompressible, diffusion coefficients for liquids, it is almost independent of pressure. And you will come to know shortly in the equations that are proposed for estimating diffusion coefficients, there is no pressure in those equations, which indicates that diffusion coefficients for liquids, they are independent of pressure. And what is the reason for that? The reason is we consider liquid to be incompressible. Let us move on. Now let us know few equations, important equations for estimating diffusion coefficients. So diffusion coefficients for liquids. You can estimate it in two ways. First is you can estimate those coefficients, estimate those diffusion coefficients experimentally, or you can estimate them by using equations that are proposed in the literature by various authors. Experimental values, they are highly accurate. If you are getting diffusion coefficients, if you are getting values for diffusion coefficients by carrying out experiments, then you are going to get highly accurate values of diffusion coefficients. But this experimental values, they may not be available in every situation. It may not be possible to carry out experiments in every situation. So experimental values, they may not be available in some cases. Then there you have the option of finding it by using the equations. So the values that you get by using those equations, those are theoretical values. Now these theoretical values, they are estimated by using equations that are proposed in the literature. They are less accurate as compared to those for gases. That means the theoretical values for diffusion coefficients of gases and theoretical values of diffusion coefficients for liquids, if you compare them, then for gases you will be having more accurate theoretical values. For liquids, the accuracy is somewhat less. And what is the reason for that? The reason is, for liquids, you don't have any sound theory about the structure of liquids. There is no any sound theory that is available which describes the structure of liquids. Like for gases, you have the kinetic theory of gases. So kinetic theory of gases, since most of the equations for gases, they are based on kinetic theory of gases, they are more accurate. And as for liquids, we don't have a sound theory about the structure of the liquids. the theoretical values are less accurate as compared to those of gases. Let us move ahead. Now let us know few equations. So first one is a correlation that was proposed by two persons, Wilke and Chang. So let us know what is the Wilke and Chang correlation. This correlation or this equation is an empirical equation which can be used for dilute solutions of non-electrolytes. So Wilke and Chang equations or correlation, it is useful for, or it can be used for dilute solutions of non-electrolytes. And what is this equation? And if you have the case where solute A is diffusing in solvent B, then the correlation proposed by Wilke and Chang is this one. DAB is equal to 117.3 into 10 to the power minus 18 into 5B into MB raised to 0.5 into T divided by mu into Va raised to 0.6. So you can see there is no P pressure in this equation, which indicates that diffusion coefficients for liquids, they are independent of pressure. Now in this equation, DAB is of course the diffusion coefficient in meter square per second. Then MB is the molecular weight of B, which is the solvent. And then T is the temperature, absolute temperature in Kelvin. Mu is viscosity of the solution, and that has to be in kg per meter per second. And if you are dealing with dilute solution, so you have solution of A and B, where A is the solute and B is the solvent. And if this is a dilute solution, that means if this is a dilute solution, B, the quantity of B will be very large as compared to that of B. So in that case, for dilute solution, the viscosity of that solution is approximately equal to viscosity of the solvent. So mu, even though we are saying it to be viscosity of solution, you can take it as viscosity of the solvent. Why? Because it is this equation is applicable for dilute solutions. So we will understand it in my next video lecture. I will be discussing three numericals based on the estimation of diffusion coefficients for liquids. For time being, let us know those equations. Let me erase this. So mu is viscosity of the solution in kg per meter per second. Va is molar volume of A, that is molar volume of solute, that too in meter cube per kilomole at the normal boiling point of the solute. So Va is molar volume of A in meter cube per kilomole at its normal boiling point, or the boiling point at atmospheric pressure, at 1 atmosphere. Normal boiling point is the boiling point at 1 atmosphere pressure. Then 5B, this parameter, it is called association factor for B. So different solvents will have different association factors. We are going to know the values for this association factor for few important solvents. Then the association factor for few solvents, 5B. So I have shown it in this table. So let us know for few important solvents. So if it is water, then phi is 2.26. If it is methanol, then phi is 1.9. And if it is ethanol, then phi is 1.5. So different solvents will have different values for this phi. What is phi? The association factor. For non-associating solvents, then you can take phi B as 1. So if the solvent is non-associating, then phi B is equal to 1. So what are this few examples of non-associating solvents? for which phi b will be equal to 1. So you have benzene, you have ethyl, ether, then you have these are the solvents for which phi b is 1, or these solvents are non-associating solvents. Then the problem with this equation, the equation proposed by Wilke and Chang, you cannot use this equation for solutions with viscosities greater than 0.1 kg per meter per second. So if viscosity of the solution is greater than 0.1 kg per meter per second, then the equation, Wilke and Chang equation, may not give you the correct values. So you have to take care that while using this equation, you have to ensure that the viscosity is less than 0.1 kg per meter per second. Let us move on. Now in this equation, MB, molecular weight of B, phi B, the association factor for B, and VA, the molar volume for A, these are constants. That means, according to this equation, DAB is proportional to T, and it is inversely proportional to mu. So you can write DAB is directly proportional to T and inversely proportional to mu, or DAB is directly proportional to T upon mu. So this relationship will be useful in estimating diffusion coefficients at different temperatures. So for example, diffusion coefficient at one temperature and hence with one viscosity is known to you, then you can use this relationship for getting the diffusion coefficient at some other temperature. So as per this equation, DAB is directly proportional to T and inversely proportional to viscosity. Let us move ahead. Then the other equation that is available, it was proposed by Stokes and Einstein. So it is Stokes-Einstein equation. So it was derived for very large spherical molecule of A that is diffusing in a liquid solvent of B, liquid solvent that is B, whose molecules are small. So Stokes-Einstein equation, it was derived for a very large spherical molecule of E diffusing in a liquid solvent B, which is of small molecules, or molecules of solvent B are small as compared to those of the diffusing solid. So in this derivation, all molecules are assumed to be alike and they are arranged in a cubic lattice. So this equation assumes that all molecules are alike and they are arranged in a cubic lattice. Then the equation is DAB is equal to 9.96 into 10 to the power minus 16 into T divided by mu into VA raised to 1 by 3. So in this equation, DAB is the diffusion coefficient in meter square per second. Then T is absolute temperature in Kelvin. Mu is viscosity of the solution in kg per meter per second, and VA is molar volume of E in meter cube per kilomole at its normal boiling point. So this is the equation that is proposed by Stokes and Einstein. It is applicable for the case where large solute molecules are diffusing through small solvent molecules. Let us move on. Now in this equation, VA is constant, 9.96 into 10 to the power minus 6. Again, this is a constant. That means, according to this equation, DAB is proportional to T and it is inversely proportional to mu. That is, according to this equation as well, DAB is directly proportional to T upon mu. So if DAB at one temperature is known to you, you can find DAB at other temperature by using this relationship. Let us move on. Then there is another equation which is proposed by Hayduk and Laude. So Hayduk and Laude equation. So this equation was derived for dilute aqueous solutions of non-electrolytes. So in this case, the solvent is always water. The Hajduk and Laude equation, it is derived for dilute aqueous solutions of non-electrolytes. And what is this equation? DAB is equal to 13.26 into 10 to the power minus 5 divided by mu B raised to 1.14 into VA raised to 0.589. And you can observe there is no temperature in this equation. So here DAB is diffusion coefficient in centimeters square per second in this equation. Mu B is viscosity of water because the solution is aqueous, and but this the equation, the viscosity has to be used in centipoise. Then VA is molar volume of A in centimeter cube per gram mole at its normal boiling point. So this is another equation that can be used for dilute aqueous solutions for finding out diffusion coefficients for solute diffusing through water. So this is another equation. Let us move on. Now dilute liquid solutions, you have two cases. If you consider two components A and B, then you have dilute liquid solution of A in B and then B in A. So one is solution of A in B where A is solute and B is solvent, and the other case is B is solute and A is solvent. The role has changed. Now solvent has become solute and solute has become solvent. So in this case, DAB in the above two cases are different. So DAB in the first case where A is in a dilute solution with B and B is in a dilute solution with A. In both the cases, DAB will be different. Why it is different? Because when you change the rule, that is solute becomes solvent and solvent becomes solute, then viscosity, molecular weight and B, they are different when A and B are exchanged. So that's why you have different values for these two cases. But this is not the case with gases, with binary gases. This is true for liquids, but for binary gases, this is not true. In both the cases, for binary gas mixtures, DAB will be same. So with this, I end my discussion for estimation of diffusion coefficients for liquids. Here I have discussed important equations that can be used for estimating diffusion coefficients for liquids. I hope you have understood those equations. If you have any doubts, please mention them in the comment section. So thanks for watching this video lecture. In my next video lecture, I will be discussing numerical examples based on this equation. Do subscribe to my channel. Tell your friends to subscribe to it. Hit the bell icon so that you'll be notified as soon as I upload any new video on my YouTube channel. Hope to see you soon in my next video lecture where I will discuss numerical examples for estimating or numerical examples based on the estimation of diffusion coefficients for liquids. For now, have a nice day. Bye bye.